Swayam Prabha. Digital India. Educated India.
So, welcome back everybody to the last lecture on Introduction to Soft Matter, and in the last class we were discussing the idea of the complex modulus, and we had stopped at a particular problem. The problem was the idea of the Maxwell fluid, where we took the governing equation in the format of P1 Q sigma dot plus P naught sigma equal to Q1 epsilon dot, right. And we were asked to, the idea is to find out the complex modulus for this particular situation. So, we have already established that this formula is correct, where G star omega is given by this set of terms on the right hand side. Now, for the case of the Maxwell fluid, we know that this particular term is not there. So, we do not have to worry about this term, we only have to evaluate this particular integral. And we had seen in the last class also that this quantity delta Gs here is of this particular format, right. So, we should go ahead and just complete this integration in that case. So, let us just go ahead and do that. So, now you have I omega, and this is integral 0 to infinity, and we replace the quantity that we already have for delta Gs, and we can just write it as Q1 by P1 e to the power minus P 0 by P 1 s into e to the power minus I omega s ds. Right. And if you evaluate this particular integral, you should find that this integral comes out to be Q1 I omega. So, Q1 is in the numerator, and in the denominator you will end up getting P 0 plus P 1 into I omega. Now, this is a complex number. You can keep it in this form, or you can go ahead and simplify it further. If you want to simplify it and express it as a proper complex number, then you have to get rid of the denominator, the complex numbers in the denominator, and what you can do is you can simply multiply the denominator by its complex conjugate, right. So, you can go ahead and do this, you can multiply it this I omega. So, you have P naught plus minus P 1 I omega, and in the bottom you are going to multiply the conjugate with the original term, and what you are going to get is P 0 plus P 1 on all these are squared, right. And here, I mean, you can simplify it a little bit further if you want to. You will have Q1, and you can take this I omega inside. So, if you do that, you will end up with P 1 omega square plus P naught I omega, and in the denominator you have, right. So, you have basically gotten rid of the complex number from the denominator, and now you have the function G star as a complex number itself, right. So, this is the solution that we are looking for. Now, for a Maxwell model, you obviously know what these P 1, P naught, Q 1 are, and you can go ahead and replace these, and you can evaluate that for the model that you have built. Now, there is one more way of getting to the same solution, and that for that, so just consider a situation where the transients have died out. Your input was a sinusoidal wave, right. So, your input was, so an alternate method is we have the input is a sinusoidal function. So, your epsilon t is equal to epsilon naught e to the power I omega t, and in this case we know that your stress will be g star omega epsilon 0 e to the power I omega t. Okay. This is the situation when the transients have died out, leaving the steady state response. Right. So, if you consider back the equation of that form that we had taken. So, for an equation of the form that we had taken, we had taken P 1 sigma dot plus P 0 sigma equal to Q 1 epsilon dot. In this kind of a case, you can just go ahead and replace, since you know the functional forms, you can just go ahead and replace sigma t and epsilon t. These are the derivatives. So, if you replace these sigma comma sigma dot and epsilon dot, then you will get a case where you have a derivative of sigma. So, here you will actually end up multiplying this with I omega, and this will be g star epsilon 0 e to the power I omega t. So, your left hand side will be this, and on your right hand side you will have q 1 epsilon 0 e I omega t. Right. So, you can eliminate these terms, and this will basically give you the g star omega as, sorry, I have missed out an I omega term here because this was an epsilon dot. Okay. So, I have missed out an I omega. So, this will be q 1 I omega, p 1 I omega plus p naught, which is back to the same form, right. We can just double check, right. So, this is what we got by evaluating the integral, and by a more direct method we got the same result. So, the direct solution suggests an important generalization, right. So, what do you see here? You see that if you have a derivative, then you can replace this entire quantity, the derivative part, by I omega, and you can rewrite the original polynomial form. In this, you can keep the original polynomial form, right. So, basically what I am saying here is, note that if you use the operator form, then in the operator form the previous equation can be written as P 1 d plus P naught of sigma equal to Q 1 d epsilon, right. So, in this expression, to get the answer, the correct set your d as I omega, or set d as I omega and epsilon as 1. So, you just take the previous equation, set d as I omega here and set epsilon as 1, and you can get back the same form of g star, right. And we have to set one more thing, we have to set this sigma as g star. So, in the generalized case you can show in the general case of governing equation being P d sigma equal to Q d epsilon, you can show that G star omega is nothing but Q of I omega to P of I omega. Right. One more last quick sample problem. And we have let us say the from the Kelvin Voigt Mayer body you have P naught sigma equal to Q naught epsilon plus Q 1 epsilon dot, right. So, this is the governing equation for the Kelvin Mayer Voigt body. So, in that case if you just apply this idea, this makes it very straightforward, this generalization. So, if you apply this generalization you can easily see that your complex modulus now becomes this particular form. Here I only have to replace the derivative operator by I omega, right. So, I will have Q naught plus Q 1 I omega, and on the left hand side I only had P naught, there is no derivative term here. So, P naught, and this is your answer. And please note that this complex modulus term contains both the storage and the loss moduli, right. So, we have come a long way in this particular course. We have discussed quite a few topics, and these two sample problems were meant to wrap up the course. And before we finish the lecture, what I would like to do is I would like to quickly go over all the different things that we have discussed. Okay. So, what I have done is I have prepared a PPT format where all the things that we discussed from the beginning of the class we have sort of summarized here, so that we can quickly go over it and evaluate what we have learned in the class, right. So, we started off in the beginning of the class by discussing some important definitions, which included definitions of soft condensed matter, colloids, viscoelasticity. We discussed the idea of natural time scales in a historical context, and we discussed the historical context for the definition of the Deborah number as well. And we also discussed the differentiation between the Deborah number and the Wiesenberg number, right. And once we did that, we decided to take a macroscopic formulation for viscoelasticity, and we saw that the basis of that can be tested by 6 important tests, including the stress control test, the release of stress, the strain control test, and the effect of different histories, energy dissipation, and effect of sinusoidal oscillations. So, we did not touch upon energy dissipation too much in this particular course. That can be done in a more advanced level course, but we did touch upon at the very end. We also discussed the idea of the sinusoidal oscillations, although initially we had started with the stress response and the strain control test. So, the next thing we discussed was the step stress test, and we saw that the 3 important behaviors, that of the classical elastic solid, for example here. So, the classical elastic solid, when you put a step stress, then the response is actually rather simple, right, and this is something that you have already been familiar with. We also discussed the behavior of the classical viscous fluid, where when you put a step stress, then the viscous fluid continuously strains, right. So, your the fluid, this basically encapsulates the idea that a fluid cannot withstand shear. Now, these two together, the classical elastic and the classical viscous, in some senses when you put these responses together, becomes the response of a viscoelastic material, because it has both the term visco and the elastic. And this is the response to a stepped stress test, where we see that when you apply a stress, you have an immediate solid like response from 0 to A, and then you had a continuous straining from A to B. And then when you relax, when the stress is taken away, then the strain slowly decays, and this can go down, decay to 0, or it can decay to a non-zero value. So, this can either be 0 or a non-zero value, right. So, or non-zero, depending on the situation. Okay. Next, the other important test was the step strain test, where again we saw and we understood the response of a viscoelastic material in terms of the responses of the classical elastic solid and the classical viscous fluid. Okay. And the important thing here to note was that when you have a viscoelastic fluid and you apply a step strain, then the stress decreases, and this is the very classical stress relaxation phenomena. Right. And these two tests together, the fact that you can have a material that is continuously straining under applied constant stress, and the fact that you can have a decay in stress when you have apply a constant strain, this led us to develop two important concepts, which is the concepts of the creep function and the stress relaxation function. Now, the creep function here J and these two here in the brackets implies that J is a function of the applied stress and is also a function of time. When the idea of linear scaling or the principle of linear scaling is valid, then you can divide this function J by sigma, and you get a function that is only dependent upon time. Okay. And this became the creep modulus. Similarly, for the stress relaxation phenomena, if the principle of linear scaling is valid, then you can divide the function g. Here the function g is a function of two important parameters, the strain and the time, and when you divide it and assuming that linear scaling is valid, you end up getting a function which is only a function of time now. So, this is one of the singular important aspects that we covered in this particular course. Once we did that, we tried to familiarize ourselves as to why this sort of happens, and we discussed because we already know that soft material refers to a collective of many different types of materials. We tried to discuss the different types of materials that fall under this category. So, we discussed polymers, we discussed surfactants and liquid crystals. To discuss these, we also discussed the preliminary ideas of the interatomic bonds and how they are relevant here. This does not obviously reflect an exhaustive list, but polymers are one of the most widely used materials nowadays in industry. So, we discussed that in a little bit more detail. So, we for example discussed the idea of molecular weight calculations of polymers, for example the weight averaged molecular weight, this is the viscosity averaged molecular weight, and other important parameters are associated with it. After that, we moved on to distinguish an important set of equations which is called the constitutive equation. So, we first started off with understanding that they are different than the conservation laws, and then we enumerated many of the important constitutive equations that we find ourselves commonly in solid and fluid mechanics. For example, the perfect fluid, right, and the Hookean solid, and obviously the Newtonian fluid. And here once you use this constitutive equation, you will end up with the Navier-Stokes equation once you do the proper formulation for the conservation of linear momentum. The two important models here listed here, the Carew model and the power law fluid. Now, these were two inelastic models that we discussed, and they were really important introductions into this behavior of different types of soft materials such as polymers. Right? They are called inelastic because they do not have the elastic term in them, but still the fact that the viscosity varies as a function of shear rate was an important understanding, and these models are very, very useful. From that we went on to understand the concept of simple shear flows and related concepts of normal stress differences, right. So, we saw that in certain fluids you can have in the stress tensor can have normal stress differences, and we encountered these particular functions where N1 is the first normal stress difference and N2 is the second normal stress difference. We familiarized ourselves with we saw some experimental results on the rod climbing effect, and this is a very classical effect whenever it comes to polymers and viscoelastic materials. With this introduction to constitutive equations, we started our journey into the viscoelastic domain, right, and we started it with the simplest of the possible models, which is called the Maxwell model. And in the Maxwell model, we in fact looked at the original paper of Maxwell, and the model is rather simple because it only has a spring and a dashpot, and the spring constant and the parameters of the dashpot, they take into account, together they make up the viscoelastic model. Right. Here the spring and the dashpot are placed in series, and we saw a similar another model, which is Kelvin-Voigt-Mayer body, but here the spring and the dashpot are now in parallel. So, these were the two of the simplest possible viscoelastic models, and then we built using more complex models using this. For example, various 3 parameters models were built, for example, Jeffrey's fluid, and then we went on to understand models which have many different springs and dashpots together to make a more complex constitutive equation. Now, please note that all these specified models are linear viscoelastic models, and these are all one dimensional models. Right. So, with that so with the last part that we are discussing towards that, the use of n springs and n dashpots, that helped us arrive at a general constitutive equation, where we saw that the stress and the strain can be related by in a polynomial type of form, where this coefficient is basically consists of the multiplier of the stress here consists of many coefficients and the differential and powers of the differential operator. Now, these exact values of Pn, Pn minus 1 or Q naught, etc., depends upon the kind of model that you have used, and you can use, and we saw how to derive this particular equation in different contexts. We also saw the response to the arbitrary stress history is given by this particular equation right here. Similarly, the response to the arbitrary strain history is given by this particular equation right here. We also familiarize ourselves with different variations of these equations, because this term here it represents a convolution. You can have different variations which are equivalent in nature. I also discussed that in some books, instead of 0 plus, you have the lower bound is the lower limit starts from minus infinity, and in this case this first term is not required. Then, to cement our understanding of these constitutive relationships, we moved into a slightly more advanced topic of what is called objectivity, and we saw that different scalar quantities like density, etc., those are frame invariant, right, and they are objective by themselves. But vectors are objective if they transform according to this particular law, where these are the transformed components, and Q is a rotational tensor. So, basically this is an orthogonal tensor, right. And if a vector transforms according to this particular law, it is called objective or frame indifferent. Similarly, a tensor has to obey this particular rule if it is to be frame invariant or frame indifferent. Now, the reason we are looking at this is because we realize that the time derivative of the stress tensor is not objective, right, and the time derivative of the stress tensor occurs in the some of the models that we had discussed previously. So, that so this basically serves as an introduction to the ideas of continuum mechanics, where there are objective derivatives, and we did not go into depths of that, but Alderide was one of the pioneers of this, and the Alderide AB fluids use objective derivatives, and there are other type of viscoelastic models which also employ objective derivatives. We did not do this in this particular course, but this is a logical conclusion of what we had discussed, and you can take up this in a more advanced course on this particular topic. After that, as in this course, in the very beginning of this course, we had said that we should understand material properties not only as being time dependent variables, but also as frequency dependent variables. So, we looked at response to sinusoidal oscillations, and we asked ourselves the question that if a viscoelastic material is subjected to a sinusoidal oscillation where the input of strain is a sinusoidal function, then what will be the corresponding output? And we found out that the corresponding output occurs in the form of this equation here, equation 4, where this term G dash is also called the storage modulus. The term G double dash is called the loss modulus, and under certain assumptions you can relate the particular form of the stress relaxation function to G dash and G double dash by this important integral equations right here. We also saw that for viscoelastic material, there is always a phase difference between the input and the output, and the phase difference is given by this particular form, where del W del is the phase difference, and it is given as the tan inverse of G double dash by G dash. Here the fact that we have omega in the in brackets refers to the idea that G dash and G double dash are functions of the imposed frequency omega. The same formulation that we did previously can be written in the complex form, and if we choose to write the input in this particular form, where I is the complex number. So, epsilon naught e to the power I omega s, this is now a complex number, but the complex number has cosine and sine forms, which are, so basically you still have the time dependent oscillations. Then the corresponding output can be written in this particular form. This is a very simple equation here, but G dash now is a complex number, sorry, this is G star, not G dash. G star is now a complex number, and this complex number is also called the complex modulus, and this is given as G dash plus I G double dash. Right. Once again, please, I here is the complex number or root over of -1. Now, this G dash or the complex modulus is a material property, and we also looked at two other material properties, which are dynamic viscosity defined as G double dash by omega, and the complex viscosity, which is defined as G star by omega. And so that's sorry. So that sums up about almost all the things that we covered in this particular course, and as I said, this is a beginning level course. So you are probably some of you who are taking this course are probably going to take courses on rheology, etc., and hopefully that will be very helpful. The contents of this course will be very helpful to you. Now, I'd like to just include two more important notes for clarification, and that is, we had initially used the symbol mu for viscosity, and a few lectures later we changed it to eta for viscosity. So this slight discrepancy is there, and in the integration of the stress relaxation function and the creep function, we have, or many times we have used S as a dummy variable for integrations, and the dummy variable S is used in the time sense. But it is different than the variable used in Laplace transforms. So we use the Laplace transforms to solve some of the equations, and there also an S appeared, but the two S's are different. One is in the Laplace domain and the other is in the time domain. Okay. So with this note, I would like to conclude, And what we have done is in this entire course we have gone through quite a lot of material. Our biggest focus was on understanding the phenomena of creep and this phenomena of stress relaxation that we kept seeing in different forms. Even when we are discussing the different viscoelastic models, our focus was still on understanding the creep function and the stress relaxation function for those models. Right? So, this course, as I had said earlier, also is a beginning level course, and it is meant to familiarize yourself with the various terms that are used in this area, and hopefully you are going to take more advanced level courses in this. For example, courses on rheology or courses on condensed matter physics or viscoelasticity, etc. And I hope that this course, the contents of this course will be very useful to you in understanding the area of soft materials, and if you decide to take advanced courses, the material covered hopefully would be extremely helpful and advantageous to you. So with this we are ready to end this course, and thank you very much for your time, and good luck. Okay.